All right. Okay, let's start. Hello, everybody, once again. How are we doing? It's okay today? Nice. Ready for weekend, probably, yeah. But before that, unfortunately, discussion with me. Sorry. Okay, this is plan for today. Today we will focus on two things: projectile motion uh, and projectile motion, and also there will be one D motion. Okay. So we have example number 1, 2, and 3. I think I can cover it all. We can do it today. Yeah. So example number 1 and 3 are projectile motion, and example number 2 is 1D motion. Quick reminder, I hope that you keep in mind that you should it's better for, I think for us, for me and for you, that you familiarize yourself with the problem statements before coming here, yeah? Because there's it's beneficial for you, I think, because what's the point of us spending our time on reading in these discussions, yeah? Let's maybe spend that time on more productive things like solving them, yeah? So that's why I think that it's also beneficial for you guys, that you don't waste we don't waste our time here. And plus that thing about solution manuals, I think this is the worst thing you guys can do this semester, to instead of thinking on your homework problems, just go for ready to go solutions. Yeah, I think it's crazy basically. Yeah. Okay. Without further ado, example number 1. Yeah. Or actually, there's one more hidden part. Are there any questions to what we covered last time? Any? Do you have any questions? Or everything is fine? No, okay. How about logistics? Did I forget about anything when it comes to logistics? Yeah. Did I cover everything? Okay, example number 1. So let's briefly familiarize ourselves with the problem statement. Okay, so basically it's clearly a projectile motion. Yes, we have a thing that is fired from here, yeah, from point A. This is the trajectory. Yeah, something like that. And basically they gave, what did they give us? Initial velocity. We know that we are on Earth, so this is our gravity. We know the geometry. Yeah, and they just ask us to find this distance. Yeah, the distance d. Yeah. By the way, before coming here, I also defined this parameter h. And that parameter is obviously d times tangent 10 degrees. Yes, based on this triangle. Based on this triangle, we can come up with this expression. Okay. Okay, so let's find the solution. Okay, and while working on the solution, I would like to take an attendance. So exactly last time, number 1, your name and last name, number 2, your name and last name. Thank you so much. Okay, so this is how I approach to these problems. So I just would like to express the motion in the x direction. In the x direction. So what is the acceleration in the x direction? I believe it's 0, yeah? And by the way, it's not only 0, but it is also constant. So we can use those simplified equations. We don't have to integrate, yes, in here, because we know the explicit form of the velocity. Yeah, if a is constant, this is velocity. Vx will be v0x plus axt. Yeah, okay. I said that this is 0, so we can get rid of that, and let's maybe quickly find Vx0. So I believe I have to do these two projections. Yeah, so this will be V0 cosine alpha. yeah, and this there will be V0 sine alpha. Okay, and we know all of that, yeah, so basically V0 x is V0 cosine alpha, plug in values, and you can obtain that this is equal to approximately 241.481 feet per second, and V0y is 0 sine alpha, plug in values, and this is approximately 64,705 feet per second. Okay, so our Vx is basically V0x, which is constant, 241,481 feet per second. Okay, we're done with velocity. Yeah, this is our expression for velocity. Now position. So if I remember correctly, this is expression for position. x0, but only if acceleration is constant, okay? For the third time today, only if acceleration is constant. If it's not constant, you integrate, okay? V0xt plus 1/2 axt squared. Okay, this is our general form. Let's fill it out. This is 0, as we said. This is known. And this is also 0, yeah? Because of our coordinate system, yes? Our coordinate system starts from 0. So this is our expression for Vx, for x. X of t is basically V0xt. That's all. Okay, guys, we're done with the x direction. Any questions? Yeah. So now, analogical thing in the y direction. Okay, ay is equal to minus g, right? Yeah, and by the way, it is also constant. So I'm just going to repeat exactly the same expressions, okay? Okay, we are done with our velocity. Now position. Okay, let's again fill out our expression. So that was minus g, and that was 0. So our y of t is V0 yt minus 1/2 gt. And I see that I forgot a squaring here, yes? Yeah, should be squared. Okay, guys. Great, we are done with integrating. So they ask us to find this distance. So how can I do it? I would like to use these two expressions. I would like to use these two expressions, this one and this one. And maybe some of you can tell me, I will just have one question here. Can anybody tell me how to find that parameter d, the distance d, if I'm using these two expressions for positions? I bet all of my money that you know it. Yes?
When you find the point of placement of y, which is h, you know, you can find it.
Okay, and I will have time. I will have time, basically. Yeah, yeah, I will have time. Yeah, and then I can plug in that time in the other equation.
Right,
Yes, yeah. And instead of x, I can put there d.
Right.
Okay, so thank you for being right, because I would lose all of my money. Okay, so let's do it. Basically, let's do it. Yeah. So yeah. So basically, let's say that point B. So this point B. Yeah, I will put it in. You are right, of course. I will put it in just more mathematical formalism. Okay, so that point B is reached at time t star. Let's say. Okay, so let's write that point B. Point B is reached at time t star. Okay, so that means that when it comes to x, so I can write that d is equal to v0x t star. Yeah, or we can basically write in here that x of t star is d and y of t star is minus h. Yeah, so minus h, or thank you, yeah, minus d 10 degrees is equal to v0y t star minus 1/2 g t squared t star, of course. Okay, so these are two equations and two unknowns, and you guys solved that type of set of equations 700 times in your life. Is it true? That's true. Two equations, two unknowns. So because unknown is this thing, and this is unknown, yeah, and this unknown. Okay, let's solve it quickly. So t star is equal to d divided by v0x, and let's plug this one in the second expression. So we will have basically minus d 10 of 10 degrees, and this is equal to d v0y v0x minus 1/2 g 1 divided by v0x squared d squared. Okay, d cancels out almost everywhere, and our d has this expression 2v0x squared divided by g tangent of 10 degrees plus v0y v0x. Okay, and grab your calculators and obtain that our d is approximately 1609 period 143 feet. Answer. Okay, questions? Sure, that's a good question, because our coordinate system is placed here. Okay, this is where our coordinate is, and our motion starts from point A. Could you please give me coordinates of point A expressed in this coordinate system? 0, 0. Does this answer your question? Yeah. I'm glad to hear that. Yeah. Another question? Was it easy? Okay, great. So what? Example number 2? Let's do it. Example number 2 is tricky, but let's see. Let's familiarize ourselves with the problem statement, okay? Very quickly. All right. I would like to start, but I see that some of you are still writing, so I can wait like a couple of seconds. No worries. Okay, you can still write. I will be talking. I hope you don't mind. Can I? Yeah. Okay. So what do we have in here? Aha, we have a sphere. Yeah, and that sphere basically can move. They told us here. Yeah, they told us it here. Yeah, and I also wrote it down here. Yeah, that sphere can basically move in this region. Yeah. It can move here, maybe it will go like that, maybe it will go here, maybe it will go left, then right, then it will like stay here a little bit, then it will go left again, and then it will go right, okay? Yeah, this is like our motion. It will go like back and forth, yeah? And it doesn't have to be oscillator, it doesn't have to be like that nice motion, no? Back and forth. It can do whatever it wants, but it cannot leave that region, yes? Okay. Yeah, I'm talking about it because yesterday I had to like think a little bit before I understand that problem, okay? So we know that. We also know, they told us that this is acceleration, expression for acceleration, okay? Okay, that's good to know. And it's, by the way, it's explicit form, so we like it, if it's given explicitly, yeah? And they told us that we should tell them what is the range of motion. So for example, so basically, what is the range of motion? So within this visibility region, that ball will have like one more constraint. Okay, it will just go only here, for example. Only here. It will not leave that spot. Okay? And they told us basically to find the bounds. Yeah, what is this bound and what is this bound? They told us to find those two values. And they told us that our sphere starts from S equals to delta 4, so from here, yeah? This is, sorry, delta, lambda, of course, yeah? Lambda 4 divided by 4, and we know that its velocity is 0. So we are going to release our sphere from here with velocity 0, and they told us to find these two bounds, that bound and that bound. Okay? I have a strange feeling that I'm talking too much. Yeah, but are you with me, guys? Yeah, yeah. So besides position and velocity, let's also find acceleration at that point. Okay, it's by the way 8 meters per second. But let me prove it to you. Okay, so let's take our a. 2 pi divided by lambda. Yeah, and instead of s, I'm going to just plug there lambda 4. Okay, so that would be basically a0 sine pi half. So this is a0. Yeah, this is 8 meters per second squared. Yeah, because they told us what is a0. Yeah, here. Okay, so that means that our sphere will go to the right. Yeah. Yeah, it won't move to the left. It will accelerate to the right. Okay. So this is everything we know, and now let's start solution. So I would like to integrate right away. So I would like to do that. And please observe that in here our acceleration is a function of position. Yeah. So every time I see that, I do not want to go for this definition of acceleration. Okay. I think Professor Sunny did it on the lecture. We can actually modify this thing if we multiply it by 1. Yeah. So we can do dv dt, and I can multiply it by 1. I think I can put ds in here and the ds in here. Yeah, I kept the balance. Yeah. So, and this is velocity basically. Yeah, this is velocity. So this is basically velocity dv ds. Okay. So let's maybe use this expression here. Okay, and now again, as last time, everything with S on one side, everything with V on the other side. And let's integrate. Okay, I believe they told us that our velocity is 0 at the beginning, and our position is lambda divided by 4. Yeah, and we will end up with some velocity at some position. Okay, so we basically have 1/2 v squared in here, and in here we will have, if I remember correctly from school, a0 lambda divided by 2 pi, negative cosine 2 pi s lambda from lambda 4 to that. Yep. Okay, let's plug in our integration bounds. So we'll basically have 1/2 v squared, and this is equal to minus a0 lambda 2 pi cosine 2 pi s lambda plus a0 lambda 2 pi cosine 2 pi 4 divided by lambda. Aha, so this is 0 basically, because yeah, this argument is pi over 2, yeah, and cosine of pi over 2 is 0, yeah, so we can basically get rid of that. Yeah, I believe I can also get rid of that half. We don't have to, but we can. Yeah, like we don't need that. It doesn't matter. This one, and this one. Yeah, it can stay. Okay, but anyway, yesterday at home. No, 2 days ago. 2 days ago, 2 days ago I solved it. So 2 days ago I just asked myself, what is the next step? And I noticed that the left-hand side is always positive. Do you see that, guys? That this guy is always larger or equal to 0. It has to be, yeah? However, on the left-hand side, we have negative sign, yeah? All of these guys are positive. So we have to have a requirement. Cosine must be lower equals 0 in order to this to be consistent, yeah? So let's draw cosine very quickly. If I remember correctly, this is how cosine look like. Yeah, x cosine x. This is pi over 2. This is 3 pi over 2. This is minus pi over 2. And this is minus 1.5 pi. Yeah, okay. So basically, our argument, 2 pi s lambda has these bounds. It has to be lower than, 3 pi over 2 plus 2 kp, where k is natural, and it has to be larger than pi over 2 plus 2 kp. Okay. Let's let's just multiply by lambda divided by 2 pi. Okay, and we will end up with something like that. Lambda plus lambda k s 3, 4. Oh, that's strange. Sorry, lambda divided by 4. Plus lambda k. So this is our expression for S. Okay. So basically, for k equals to 0, yeah, we have something like that. Yeah, and also I think that we can also plug. It will be also fine if we plug k minus 1. And it doesn't make any sense to plug there any other k. Why? Because I will steal this drawing, okay? I like that drawing. Yeah, wait a second. Because we have lambda quarter plus k lambda. So if k is 0, I just hide this one.
On the right side, though.
Because I forgot about it.
Okay.
Yeah. Great eye. Thank you so much. Yeah. Thanks, guys. Thank you for monitoring. Yeah. I make mistakes, by the way. Yeah. Also, last time I made a mistake. It's not 96, but minus 96 in the velocity. You will. Yeah. It should be negative 96. Some of you probably noticed that, but you were too nice to say it out loud. Thank you. Yeah. Okay, guys. So why I just focus on k equals to 0 and k equals to minus 1? Because these are the only regions in our feasibility region. Yeah, let's draw them. Yeah. So this is basically first region. Oh, you don't listen to me. Listen to me, please. This is our first feasibility region. Yeah. So this is basically from S equals to 1/4 lambda to 3/4 lambda, and this is second region that we obtained. Yeah, this is minus that and okay, guys. So one of them is physical, the other one is not physical. Yes, the one on the left hand side is not physical. Yeah, not physical, not physical. Yeah, because we start at S equals to 1/4 lambda, yes? And our ball cannot jump all of a sudden to the other one, yes? But the other one is physical, yeah? This is physical. For two reasons. First one, we start at S equals to lambda quarter. And for second reason, our acceleration. If our acceleration points in the opposite way, it would not be physical, yes? But fortunately, our acceleration points towards that region. That's why we can accept it. Points. I forgot n. Towards the region, yeah, in the region. Okay, so what's the answer? What is S mean and what is S max? I need somebody to say it, please. Perfect. Yeah, it will be the bound. These are the bounds. Yeah. Lambda and 3/4 of lambda. Yeah. Yeah. This is our answer. Thank you so much, guys. Okay. Take your time to write down your notes. And just let me know how does it look like from your perspective. One more. A? K. Oh, it's all the natural numbers. No, not naturals. Even what's the name? What's the next? I forgot the word. So naturals are 0, 1, 2, 3, 4, 5. And what's the name of that set? -1, -2, -3, and so on. Integers. Yes. Okay. Thank you. I forgot the word. I made a mistake. I'm sorry. Not natural, of course. Integers. Thank you so much. Z, yeah. This is the sign of integers. Cheers. But I think I didn't answer your question, yes? So this, mathematically, what I wrote in here, so look, do you agree with me that cosine is negative between pi2 and 3 pi over 2, yes? However, it is also negative here. Yeah, there is a periodicity in this. There is a periodicity in this set. Yeah, so basically it's negative here, here. If I wrote it down forward, it will be negative here, here, and here. Yeah, the period is pi 2 pi. Yeah, so basically I just included in here. I included all of those sets by entering, showing here that period of 2 pi. You see that? Yeah, by saying that, I just included this set, this set, this set, and this set. Yeah, they are distant from one another by 2 pi, but I have to multiply it by k to include all of them. Did I shed some light on the problem? Awesome. Or you're just nice, probably. And what's your name? Christine. Okay, I will learn your name, guys. Don't worry. Okay. Other questions? Yeah. By the way, this is how I look like without the MS. Yeah. So if you see me on the street, just say hi. Okay. It's hard for me to recognize all of your face because of the things we have on. Okay. Was it clear? Yeah. If it's not, digest, chew on it. Okay. Digest it, chew on it, and hit us up some questions on Piazza or office hours. Okay. Okay. So what do you want to do? Do you want example number 3? Let's do it. Yeah. It's again projectile motion. So as usually, please familiarize yourself with the problem statement before we start our solution. All right. So we have basically exactly the same thing than last time, yeah? I think the only main difference is that this time we will just express stuff in this coordinate system, in that tilted coordinate system, okay? This is the only difference, yeah? Yeah, before it was like, you know, that civilized coordinate system that is not tilted. Yeah? Before we were doing this one, and this one, yeah, x and y. So again, we have some particle with velocity 0. We are on Earth, so we know g. We know the geometry. Yeah. And this time they ask us to find h max, so this distance along the q direction. Okay, so yesterday or 2 days ago when I started solving that, I just followed my routine. So I just started with in the x direction. However, after writing down all of these equations, I realized that we don't need it at all. We do not need this information at all. That problem can be solved solely if we use this information. What happens solely in the y direction? Yeah, if you want, guys, later we can fill out this. If you want, we will have time. So anyway, what happens in the y direction? Ay this time is not going to be minus g. Yeah, this time we have to do projection of g. Yes, on these two directions, on this direction and this direction. Yeah. So maybe not y even. In the q direction. Sorry, in the q direction. Yeah. So aq will be minus g cosine theta. Yeah, you can clearly see it here. Okay, and it is again constant. So let's do our velocity q. So that will be vq0 plus aqt. Okay, so let's do some projections here. So this is vq0. Okay, vq0 is, if I remember correctly from school, v0 sine, yeah, sine beta. So we will have vq of t, v0 sine beta minus g cosine theta t. Okay. This is our expression 4. Now position. Let's do yq. So that will be yq0 plus v0q t plus 1/2 aqt squared. Okay, let's fill it out again. This is 0, and the other two parameters we found earlier. So our yq is v0 sine beta t minus 1/2 g cosine theta t squared. Okay, this is our expression for qt. Okay, guys, so now we have these two expressions, and maybe one of you can tell me what to do next, how to find this h max with these two expressions. Unnecessary. H max at maximum height velocities are perfect. Exactly. Yeah. Yeah, because basically at that point, our velocity will be here. We will be pointing like that. Yeah. That would be only in the VP direction. Yes. So in the Q direction, there is no velocity. Perfect. Thank you so much. Okay, and we can find time thanks to that. Yes, let's do it. So we can write at h max vq is equal to 0. So 0 is equal to v0 sine beta minus g cosine theta t, let's say, I don't know, t max, t star, let's say t star, okay? So that h max is obtained for t star, and t star is basically equal to v0 sine beta g cosine theta. Okay, and now we know that yq of t star is basically h max. So h max is equal to v0 sine beta v0 sine beta g cosine theta minus 1/2 g cosine theta Okay, let's simplify. Yep. So just I hope that you guys see that we have basically something minus half of exactly the same thing. Yeah. So we have something minus half of exactly the same thing. So this will be basically equal to, so our h max is equal to 1/2 v0 squared sine squared beta g cosine theta. This is the answer. Okay, that's it. That's it for today. Okay, any questions? If I can stay here like for 2-3 other minutes if you want to talk with me in person, yeah. And besides, other than that, make sure that you enjoy your weekend. Thank you. Yeah, see you on Wednesday.